I'm going to do question 1e. Okay, it's this thing in the denominator which is really that's the ugly bit. So I'm going to let u equal 1 plus x to the power of 4. That means when x equals 0, u equals 1, and when x equals 1, u equals 2. U equals 2. This is going to be important for changing our limits of integration later on. The other important thing that we need is that du dx, the derivative of u with respect to x, will be 4x cubed. Okay? It'll be 4x cubed. Now, over here again, a bit of a change of colour, and we put in the limits from 0 to 1. This is actually 1 plus x to the power of 4, all to the power of minus 3. Right, I've just written that in index form. And I'm actually going to put in, down here, that means du is equal to 4x cubed dx. Now, I'm going to put in here 4x cubed dx. It's actually x cubed dx at the moment, but I'm going to put in 4x cubed dx. 4x cubed dx, but because I've made this whole thing bigger by a factor of 4, I need to get rid of that 4. I need to counteract that 4. So I just put a 1/4 out the front. And now that's counteracted. So numerically they're the same expression. And from here, we just put the pieces of the puzzle together. We have 1/4 outside of this bit here is what u is. That's 1 plus x to the power of 4. That's u. So we have u to the power of minus 3, u to the power of minus 3. 4x cubed dx is the same as du. So that's du. 4x cubed dx is the same as du. And the limits, when x is 0, u will be 1. When x is 1, then u will be 2. And now, once again, that's not a hard integral to do, is it? That's not very hard at all. We'll put the 1/4 out the front. This will be u to the power of minus 2 on minus 2 from 1 to 2. And that will be 1/4 outside of negative. I'll put all of this. I can't really, can I? So that'll be 1 on 2 times 2 squared minus the negative again, 1 on 2 times 1 squared, which is 1/4. Outside of that's 2 times minus 1/8 minus, well, it's going to be minus a minus, which is plus, plus 1/2, and minus 1/8 plus 1/2 is going to be 3/8. So we'll have 1/4 times 3/8, which will be 3 on 32. So we've now just taken this function, which looks dreadful, and we've evaluated it by making our substitution all the way through there. Let's have a go at another one. They get more interesting, and they're going to start bringing in volumes of rotation at some point in time. So I need to give you an example of the more interesting ones. Question 2a. Let's have a look at question 2a. And you know what? I'm going to put this into index form straight up. 0, 3, x. That's x squared plus 1 to the power of 3 on 2 dx. And it's this thing here that's inside the brackets. That's the thing that's ugly that we want to try and get rid of. So let's make a substitution of let u equal x squared plus 1. That means when x equals 0, u equals 1. When x equals 3, u equals 9 plus 1, 10. Alright, the next step is, so we've figured out what the boundaries, the new limits of integration will be for the function that relates to u. The next thing to do will be to find the derivative of u with respect to x will be 2x, so du is equal to 2x dx. Okay, and this is where we're going to sidestep at this point. Right, we sidestep here. We'll put the integral from 0 to 3, still keeping it all in terms of a function of x, and this is x squared plus 1 to the power of 3 on 2 x dx. But you know what I want to do is I want to put this 2 in. I want that 2 to go in there, so I've got this whole 2x dx expression. So I'm going to put the 2 in there, which means I've just changed all of that to be a factor of 2 bigger, and to bring it back down to size, I need to put a half out the front. Okay, and that should really be an equal sign. It shouldn't even be an arrow leading into that. It's an equal sign, they're equal. Now we make the substitution. So therefore we're going to have a half, and this bit here, x squared plus 1, well, we know that that's u, so that's u to the power of 3 on 2. And we know that 2x dx, well, that's what du is. So we go du here, and the limits of integration, when x is 0, we know u is 1. When x is 3, we know that u is 10. Oops, it's not very good 10, is it? And now we'll continue with this. We'll do the integration, which will be a half outside of u to the power of 5 on 2, and we're going to put 2 on 5 there, and the limits of integration. Okay, let's substitute these things in here. That's going to be 1/2 outside of, well, the 2/5, you know what, I can take that 2/5 out too. That's a common multiplier. So I'm going to take the 2/5 here out, so it's 1/2 times 2/5 outside of 10 to the power of 5 on 2 minus 1 to the power of 5 on 2. Okay, so this is 2 on 10, which is 1/5. And this will be 10 to the power of 5 is 100,000. So it's going to be the square root of 100,000 minus 1. So root, it's 100,000 to the power of 1/2. I don't know what the square root of 100,000 off the top of my head is, but it's root 100,000 minus 1, all times a fifth, because this could actually be 1/5. So maybe in this case, a decimal approximation could be a good thing. And it's probably got a decimal approximation in the textbook. Okay, it's not a nice, neat, fractional, rational answer like that. This one will be an irrational number. But that's the working, and it's the same process, no matter whether it's a rational answer or not. Let's have a look then at question 7. Okay, question 7 is a really interesting one, because now they're giving you an expression to integrate, but they want a volume of revolution in question 7. So they give you this function that y equals x square root 1 plus x cubed, 1 plus x cubed, and the limits of integration for this are meant to be from x equals 0 to x equals 2, I think, yes, from x equals 2. And it's that bit in there It's the bit that's inside the radical sign that is going to cause all the problems. This thing here is called a radical sign, in case you didn't know. The square root sign is a radical sign. So that's going to cause problems. So how about we try and make a substitution there? We're going to let u equal 1 plus x cubed, which means when x equals 0, u equals 1. When x equals 2, u equals 9. And du dx is equal to 3x squared. So du is equal to 3x squared dx. Crumbs, how does this all work out? Well, remember, it's a volume of revolution question. So I'm just going to take you back to the last exercise. For a volume of revolution, we're going to have an expression that looks like this, an integral from a to b, and it's going to be the function of x in here, all squared dx. Alright, in this case, if we looked at that, we would have that the volume is going to equal pi outside of, and the limits would have been from 0 to 2, outside of x times 1, oopsie daisies, 1 plus x cubed to the power of a half, all squared. So that's the function of x, all squared. There's the function of x, and it's all squared. The function of x, all squared. Maybe if I put it in square brackets, the correlation is a little bit clearer between the two expressions. There's the function of x, all squared, with respect to x dx. That's what we're aiming at. Let's just maybe get rid of this power here. It's not hard to get rid of that power because there's a multiplication sign there. Again, harking back to your index laws, from 0 to 2, that will be x squared outside of 1 plus x cubed, and a half times 2 is 1, so that just becomes that expression there. Alright, I'm going to rearrange this. Pi from 0 to 2 of 1 plus x cubed, x squared dx. Now what I want is I want this whole bit here to look like that whole bit there. Those two things need to look the same. So I'm going to put a 3 in here, but I've just made that whole expression 3 times bigger than it originally was. So I put a 1/3 out the front, which brings it all back down to size again. This makes it bigger, this 3 makes it bigger, so I have to put that 1/3 there to bring it back down to its same numerical size. And now how sweet is that? We have pi on 3, this bit here in the brackets, that bit is the same as u, 1 plus x cubed, that's what u is equal to. So this is u, 3x squared dx, 3x squared dx is du, and now the limits of integration with respect to u, when x was 0, u was 1, when x was 2, u was 9, and that is probably one of the simplest integrations that you'll ever have to do. It probably is. That'll be pi on 3 outside of u squared on 2 with the limits of 1 to 9. Sorry that I've run out of space here a little bit. So we'll have pi on 3 outside of 81 minus 1 on 2, which in the end will give us 40 pi on 3? Have I done that right? 9, yeah, 9, 2, 8, 9, yep, 9, 81. minus 1 is 80. 80 on 2 is 40. 40 pi on 3. So the answer is 40 pi on 3. Okay, a really, really powerful tool this one is. It's a really, really powerful tool. But it's also a complex process to get your mind around at first. But once you've got your mind around it, it's just a pattern. You just follow the same pathway round and round and round. And it's not that complex. It is initially, but it's not once you've practiced it. So again, I'll leave that one with you. Work through the worked examples. Keep looking over the video and the explanations. Hopefully that is a helpful tool. And then keep practicing the problems in the textbook. All right. Have good holidays.